Welcome back to The Explainer. Today, we're diving into something I find absolutely fascinating. How we take simple, everyday visual patterns or real-world observations and translate them into incredibly powerful predictive mathematics. Because, it's one thing to just count objects or measure distances. Anyone can do that. But it's an entirely different ballgame when you start uncovering the hidden rules governing them. So let's jump right in and see how a few simple investigations can literally change the way we approach complex problems.
Here's a quick look at our roadmap for today. We'll start with the power of patterns, specifically looking at a house of cards. Then we'll move into chessboards and formulas, modeling the real world with some physics, understanding the limits of those predictions, and finally solving equations visually using technology.
All right, part one, the power of patterns.
Let's kick things off by picturing a house of cards. If you look at our source material, a basic house of cards that's exactly 3 layers high needs 15 cards to stand up. You've got your structural tenths, your flat bases, it all adds up perfectly to 15. And hey, counting 15 cards, super easy. But what happens when we scale this whole thing up? Think about the world record, which is a massive house of cards 75 layers high. So ask yourself, how many cards would you actually need to build that? You definitely don't want to sit there manually mapping out 75 layers and counting them one by one, right? It would take forever, and honestly, one tiny mistake and you've ruined the whole count. This is exactly why we need mathematical formulas.
And this is where algebra swoops in to save the day. Instead of counting, we can just use the general formula that's derived from this pattern. C equals 1/2 n times 3n plus 1. In this equation, C is the total number of cards and n is our number of layers. By simply plugging in 75 for n, we can entirely skip the manual labor and instantly get the exact number of cards we need. Just like that, math turns an impossible, tedious counting task into a super quick calculation.
Moving right along to section 2, chessboards and formulas.
Let's check out our next visual pattern to see how this builds our mathematical understanding. We're leaving the 3D house of cards behind and looking at something flat, checkered rectangular boards. Think of a standard chessboard. It's an 8x8 square grid with alternating black and white squares, giving us exactly 64 unit squares in total. And since 64 is a nice, even number built from an even-sided grid, the colors split perfectly. You get exactly 32 black squares and 32 white squares. Really nice, neat, and beautifully symmetrical.
But look what happens when we start messing with the dimensions. The source data highlights 2 different rectangular boards. On a 30-square board, the split is perfectly even again, 15 black and 15 white. But check out the 21-square board, because we have an odd total here. We end up with an uneven distribution of 10 black squares and 11 white squares. That perfect symmetry is completely broken.
Which leads us to a really fantastic mathematical investigation. What are the exact numbers of black and white squares on any generic n by n board? Whether it's 5 by 7 or, 100 by 101, how do we formulate a rule for this? Well, the source material gives us a brilliant little tip to anchor our investigation. It says that for consistency, you should always keep the bottom right-hand square the exact same color. By fixing that one variable, the alternating pattern becomes a lot clearer, making it way easier to build our formula.
All right, on to section 3, modeling the real world.
So far, we've been looking at discrete visual patterns, like distinct cards and individual squares. But now, we're transitioning into continuous physical models. This is where the real world of physics and mathematics collide. We're looking at a standard laboratory setup, a spring attached to a clamp stand. In this experiment, different weights are hung on the end of the spring. We track the mass in grams and the extension, meaning how much the spring stretches, in centimeters. Just take a look at this data set. As we increase the mass from 50 grams all the way up to 500 grams, you can see the extension reliably increasing right along with it, from 3.1 centimeters up to 31.2 centimeters. But here's the thing. Raw data sitting in a table is just our starting point. To actually make this data useful, we have to apply a very clear 5-step mathematical method. First up, we plot a graph of the mass against the extension. Second, we describe that relationship. In this case, it looks pretty linear, right? Third, we draw a line of best fit right through the center of our data points. Fourth, we calculate the actual equation of that specific line. And finally, step 5, we use our brand new equation to predict outcomes we haven't even tested yet. We literally just turned raw physics data into a predictive mathematical model. How cool is that?
Next up, section 4, the limits of prediction.
Now, as powerful as our new equation is, we absolutely have to understand the boundaries of our model. Let's say we want to know the extension of the spring if a 275-gram mass is attached. We can use our equation with total confidence here. Why? Because 275 grams falls right in the middle of our tested data range, which, remember, went from 50 to 500. So the math is going to give us a highly accurate prediction of how long that spring will actually get. But the source text throws a massive curveball at us here. What if we added a 5-kilogram mass to that exact same spring? Think about it. That's 5,000 grams. If you just blindly plug 5,000 into our linear equation, the math will happily spit out this huge extension number. But would that equation actually be useful in the real world?
Well, no. And the crucial takeaway here is that every single mathematical model has physical limits. Dropping a 5-kilogram weight on that tiny little laboratory spring wouldn't just stretch it, it would permanently deform the metal, or honestly, just snap it right in half. That clean, linear relationship completely falls apart because the physical reality of the material itself changes. It's a vital lesson for us. Math is a perfect logical system, but the second we use it to model the real world, we have to account for real-world physical constraints.
Finally, let's hit Section 5, Solving Equations Visually.
For our last segment, we're going to explore how information and communication technology, or ICT for short, helps us visualize and solve complex math that would be an absolute nightmare to do purely by hand. The first ICT activity from our source material uses a graphing package to plot multiple inequalities on the exact same axes. Just try to picture the specific overlapping space where y is less than or equal to x, y is greater than 0, and x is less than or equal to 3, all at the exact same time. It's tough to visualize, right? But by plugging this into a graphing package, the computer just instantly plots all these overlapping boundary lines for us. Now pay really close attention to this specific instruction from the text. It says to leave unshaded the region which satisfies all of them simultaneously. This is such a brilliant visual trick. Think about it. Instead of coloring in all the correct areas and ending up with this dark, messy, overlapping ink blob on your screen, you shade out all the wrong areas. That means the clean, pristine, completely unshaded space left right in the middle is your perfect solution space. It just makes those complex boundaries instantly readable. And ICT isn't just for inequalities either. The second activity in the source shows us how graphics calculators can conquer some seriously tricky exponential equations. We're talking about equations like 4 to the power of x equals 40, or 3 to the power of x equals 17. These definitely aren't clean, simple integer powers, but by plotting the appropriate graphs on a calculator, we can visually find the exact intersection points where these equations hold true. It lets us find the precise decimal value of x without having to sit there and agonize over the laws of indices by hand.
And that essentially brings us to the end of today's explainer. From figuring out the exact formula for a giant house of cards to plotting the literal breaking point of a metal spring, we've seen firsthand how translating our observations into math gives us the unbelievable power to predict the future. Math quite literally allows us to see the invisible rules governing everything in our world. So I want to leave you with a final thought. What real-world pattern or everyday observation do you want to decode mathematically next? Think about it. Keep observing, keep questioning, and I'll catch you in the next explainer.